Hello everyone, I hope you all are doing well. This side Priya Bhatia. And in this specific video, we will start doing the implementation of whatever mathematical intuition we have covered up in our last section of the video. If you remember, till so far, I have given you the mathematical intuition behind how Adaboost works. We have seen what is alpha, what is the meaning of error, how the weights will be updated in such a way that for all the misclassified data points in our model, the weights will increase by a factor of e to the power alpha, and how the weights will be decreased for the correctly classified points by multiplying that older weight with the e to the power negative of alpha. Visually also, I have tried to demonstrate you both of these graphs, what will happen when e to the power alpha graph looks like and what will happen when e to the power negative of alpha graph looks like. Also, I have showcased you that how this in the second iteration we are picking up the you can say random elements, and because now we have specified the range and the range of the misclassified points will be very high. So chances are very high that for random iteration, my data points will fall into that specific range, right? So I think all of these things we have covered up in a great detail. One of the thing which is really important to understand is that in the entire discussion, what we have observed at the end of the day, that how basically we're combining all the weak learners to form up a strong learner. One thing which I have not talked about is that how at the end of the day, this algorithm will make the predictions. So you will observe that at the end of the day, the prediction will be either belongs to a positive class or a negative class in this Adaboost algorithm. So at the end of the day, what you will do is you will try to combine all of these values, which is for example, let's say you have trained DT1, DT2, DT3, three models you have trained. So you will see the predictions of those three models on a new set data. And then what will happen is, you know the value of alpha 1, you know the value of alpha 2, you know the value of alpha 3, which basically conveys the say of each and every model. And if the error is less, the alpha will be more. If the error is more, obviously the alpha will be less, right? So depending upon that, what you will do is you will just multiply alpha 1 with the y1 cap, which is the prediction by DT1, plus alpha 2 into y2 cap, plus alpha 3 into y3 cap. So what you are doing is you are trying to combine all of these three predictions, multiplying with the alpha and adding all of them. And then at the end of the day, you will just check that whether those predictions belongs to a positive symbol, means if it is bigger than, you can say 0, like positive inclined, or it's negative inclined. Accordingly, you can classify the data points into two categories. One is, you can say 1, and another one is 0, depending upon what kind of data you are dealing with. This is how basically the final prediction will be done. Now in today's video, I will showcase you each and everything step by step. Please make sure that before coming to this video, you already have watched my previous video. Then only you will be able to get a sense of what I'm trying to convey here. Okay. So let's get started and we'll try to see the code part of whatever mathematical intuition we have covered up till so far. So now, as you can see on the screen, we have a file available. I'm doing the code part in the Adaboost implementation Google Colab file. Here, if you can see, the very first step, as you all know, is to import all the required frameworks. So that is what we are doing here. We are importing all the required frameworks. And for the reference, I am just opening up the side by side the file which we have used or which I have made while explaining you the concept of Adaboost. The kind of table which you can see, we have feature F1 and F2, the target value, and then we are initializing the weights, doing the prediction via M1 DT1 model. After that, updating the weights, via seeing that how many of them are misclassified depending upon the value of alpha. We are just, with the help of that, getting the value of updated weights for the misclassified points also and for the correctly classified points also. Then if you remember, we are doing a normalization. After normalization, we are trying to specify in a cumulative range. And then in the next iteration, we are randomly getting the points in the range from 0 to 1. I hope you all remember. It's just a brief recap of what things we have covered up in our earlier session. So all of these steps only we will going to implement in this part. So here, first of all, if you will be able to observe, we are importing the required framework of pandas and numpy. And this ML extend.plotting is basically used to plot the decision boundaries. I will showcase you step by step. Now, what we are doing is, in this specific case, I'm not taking any real-time data. I'm just trying to work with a very small data so that we will be able to understand in a great detail that how internally things are working. That's the whole objective. So we are creating a manual data frame for now, and you can see that how can we create. We can just create via using pd.dataframe function. So this is where what we are doing is we are creating a manual, you can say, data set. That is the step number 2, which we are doing in this specific case. So for now, we are considering the number of records as 10, and we will be having 2 features, feature 1 and feature 2, and the target label is available, because I hope you all know that this ensemble techniques that we're covering up, whether it's a talk of stacking or it's a talk of boosting or bagging, all of these are a part of a supervised learning, and all of these will be able to tackle both the kind of problems in supervised. Means it will be easily able to tackle the classification problem also and regression problem also, right? So now here you can see this is how our data frame actually looks like, where we will be having feature 1, feature 2 and target. If you will try to see the shape of this specific data frame, you can clearly see that the shape is we will be having 10 number of records in total, and 3 specific columns we have, which is feature 1, feature 2 and the target column. If I just want to showcase you the relationship between the, I would say, features in a given data frame, which we have just curated. So we can showcase that via scatter plot. I hope you all know that scatter plot is basically used to convey the relationship among 2 features. And you can see one parameter in this scatter plot, which is hue. Always remember, this hue parameter will classify your data points as per the given labels available to us in our data. If you remember, in our data, we have 2 labels, which is 0 and 1. So when I'm saying hue as df of target, I'm saying that try to give me feature 1 and feature 2, feature 1 in the x-axis, feature 2 in the y-axis as mentioned in the code, and just classify the points. So here you can see when you run this code, you will be able to get this kind of a graph where, because of this hue parameter, you can see blue dots represent 0 and orange dot represents 1. If I'll just remove this, see what will happen. This will also give the same scatter plot, but now labeling is not there. We cannot classify that what the points belongs to 0, what are the points which belongs to class 1. So if at any point of time you want a labeling as well in your graph, so always go for this hue parameter, right? After this, if you remember, what was the first task in a Adaboost? That is to initialize the weight. So that is the next step, where what we are doing is we are doing a weight initialization. How basically we can do weight initialization in our very first iteration? If you remember, it is nothing but 1 upon the number of records. So weight initialization in the very first iteration in Adaboost is 1 divided by the number of records that we have, or the number of rows that we have. So that's what we are doing. We are just trying to fetch up df.shape will give you the rows and the columns. What we want is the only rows. So I have provided a parameter of 0th index, right? So this will give me the weight value. And finally, you will be able to have in your table feature 1, feature 2, the target label and the weights value, which is initially 0.1. Why 0.1 in this case? Because we have, if you remember, 10 number of records. So what my code is doing, it is just doing 1 by 10. So it will become 0.1. So this is the weight initialization of all the 10 records in a given data frame, right? In a given data frame. So this is the weight initialization. Done. Now, what is the next step? Next step is to train our model. You can say M1 with the decision tree classifier. We will take the maximum depth as 1. If you remember, I have talked about this, right? Because what we want is a weak classifier for the algorithm. So we are just importing this. I think we already have discussed in our previous modules that how basically we can train our decision tree classifier. So I'm just using the maximum depth as 1. Now what I'm doing is I'm just trying to take the initial 0 and first feature, right? It will take feature 1 and feature 2 as a x value. So basically what we are doing is we are trying to split the data into, you can say, train and test set. No, not train and test set, sorry. Into input features and target column or label, right? So this is what x indicates the input features here. X is nothing but it indicates the, you can say, input feature, and y is somehow indicates the target label, right? That is why we are saying take all the rows and give me the second specific column. So if you just count 0, 1, 2, so 2 is the target. That's what we want. If you want, you can just do one thing. You can say df dot columns. This will give you a list of the columns that we have. Now this 0 indicates feature 1, 1 indicates feature 2. So when you are saying take all the 10 records and give me the records from 0 to 1. So last one is exclusive here. And here what you are saying is just give me the target column as target. So this will happen. You can just recheck that whatever things I am saying is correct or not. For example, here you can see we are getting the value as 1,5. How? Because the very first first record of feature contains 1,5. Then you can see 2,3 is there. So you can see 2,3 is there and so on. So this is how basically we will be having the, you can say 10 records available with us, and y is the target column or target label that we have, which contains the values as 1 and 0. Now we will train our, you can say, first model, which is DT1 model. So I'm just removing this. I'm just saying that here every comment I'm just writing as a text section. We are doing a model training, and this is the first training part which we are doing. So I'm calling it as M1. Okay. So DT1 is ready with us. We will fit the decision tree classifier. And if you remember, the maximum depth of this DT1 is 1. That is why you can see that how this tree looks like. Here we just have a depth of 1. That's it, right? After that, if you remember, I have imported decision regions. Why I have imported? Here you can see. So one thing which you will observe in this part of the code is that if I will tell you that how many number of data points are the misclassified data points, I think you can clearly see here that these 3 points are the misclassified points because they should lie into this specific axis where this is the decision boundary which we have, right? So all the blue points should be towards blue side and all the yellow triangles will be at this one. So this is fine. This is not a point. So this is fine. This is fine, but there are 3 misclassified points what we have in our prediction, which we can see very clearly, right? Although I will showcase you with the numbers also the same thing. But what is the next step that we're supposed to do is this is what I will call it as a misclassified points. Can I say misclassified points? Now, what is the next task? We will update the weights of all the correctly classified points also and all the misclassified points also in such a way that the weightage of these 3 points, which are the misclassified points which we have, will be very, very high as comparable to correctly classified points that we have. So let's do that step. Maybe let's remove everything from here and let's deep dive into the next step. Now, I think after seeing this code part, things will be pretty much clear to everyone with respect to the previous session also, if there is any confusion left, right? So we are doing a prediction now, and whatever prediction we will be able to get, we are storing it here. Now, if you will be able to see, do you remember in the decision region boundary, we will be able to see 3 misclassified points. Now, what are those? I can again showcase you here again with the numbers, exact numbers we can verify. If you can see that there the target and the prediction is same. So this is correctly classified. Check the 3 misclassified points. Maybe you can pause the video. One is this where target is 1 and label is 0. Another one is 5th point where target is 1, label is 0. Another one is 7th point where target is 1, label is 0. It means these are the 3 misclassified points that we have. And I think these are the 3 points which we were seeing in the above image as well in the decision region. So now what is our next task is to evaluate the error. Now, how much is the error? Because we have 3 points and every point is having a weightage of 0.1, just add all of them, it will be 0.3, right? So we know that how basically we can evaluate the value of alpha. It is nothing but 0.5, 1 upon 2, if you remember, into natural log of 1 minus error upon error. So we can just, define a separate function for this. And now we can define this error value as 0.3. Because for now, if you will be able to see, we will be having 3 misclassified points. So what you have observed here, that here we will be having 3 misclassified points. So in this case, the error value should be equals to 0.3 because 0.1 is the individual weight. 3 misclassified points are there. So definitely it should come out to be 0.3, or you can do an individual addition also. So you will be able to get the alpha 1 as 0.4234, right? Now, as per that, what we supposed to do is we supposed to update the weights. We supposed to update the weights of, you can say, correctly classified points, and misclassified points. So here you can see very clearly, for all the correctly classified points means where the target is equal to the predicted value, we are multiplying it with e to the power negative of alpha, where alpha is 0.423. I have just taken the 3 decimal places to be very precise. And for all the misclassified points, we are multiplying with the e to the power alpha. So let's do that. And now we are applying the updated row weights in the new column creation. And here we go. We will be having now the updated weights with us. One thing which you will observe in this specific scenario is wherever the correct classification is being done, our updated weights is 0.06. And wherever there is a misclassification which is done, the updated weight is 0.15. So what you have observed, for all the points, wherever misclassification has been done, the weights are somehow having a higher value as comparable to the correctly classified points. That is the intuition. Why we are doing so? Because somehow we want to give a more weightage or more priority in the next iteration to the misclassified points in this Adaboost algorithm. I hope you all remember, right? So now one thing which you will observe again, the addition of these updated weights is not equal to 1. So we have to normalize it. How can we normalize it? Simple idea. Take a single value, divide it by the summation value of the updated weights. So what we are doing, take the individual value, divide by the sum of the total updated weights value. And in this way, you will be able to get the next particular column with you, which is the normalized weights, right? Now, if you will just add all of these values, you will get a sum as 1, right? Again, one thing you will notice, for all the misclassified points, it is 0.166. And for the correctly classified points, the weight is 0.07. Now, if you will just do the addition, just to verify, it will be equals to 1. Now, what's the next task? Next task is to curate a specific range. So this is done, where what we have done is we have tried to curate a normalized, I would say, weights so that the total sum is equal to 1. That is fine. Now the next task is to get the range, which you can say is, or you can say lower and upper bound of the normalized weights. That's what we want. So that in the next iteration, when we call the random numbers between the range from 0 to 1, 10 random samples, we will see that from which particular range it falls, and we will take that particular samples in the next iteration, right? So let's do that thing. So how can we do that? Upper range will definitely be the addition of the normalized weights. I hope you all know. And the lower range will definitely be that upper value minus the current normalized weights that we have. So in this way, we will be having the upper and lower value. And now our new data frame is ready with a proper table where we have feature 1, feature 2, actual target value, initialized weights, which is 1 upon the number of records, which is 0.1. Then after applying DT1 algorithm, we have the predicted values available with us. Then we have updated the weights via alpha, the normalized weights, then the range from lower to upper. It means that the very first range from 0 to 0.71, then 0.71 to 0.142, then 0.142 to 0.21, and so on. So again, one thing you will realize, wherever there is a misclassification, for example, in this case, the range is quite bigger, right? Similarly, in this specific case, the range is quite bigger as comparable to the correctly classified points ranges. Now, what is the next task? If you remember, now we are shifting towards the iteration 2, where the task is to create a new training set, right? Now, how can we create that? For that, we will call the random functions. It's numpy. I hope you all remember. We have a function of .random. It will just curate the random values of the indexes. Now, what we are doing is, for every specific index in the row, we are just iterating row wise, and we're just checking that in what specific range this random value of A falls in. And whatever be the range we have, we're just storing the indices of that in a list of indices. So now what will happen is, with this, you will be able to get an idea that maximum number of times our records fall in 7, 7, 7. And then 8 is there, 4 is there. So in a way, again, we will be having 10 samples. But now it might be the case. For example, here you can see we have a repetitive samples also. Chances are very high that we will have maximum samples which belongs to the misclassified points. Why? Because the range was very huge for that specific indexes. Now, with respect to this part, again, we are taking the initial 4 records of a data frame, initial 4 columns, which is feature 1, feature 2, and target and the weights. So you can see we will be having the records of 7, 8, 7, 4, 3, 9, 6, 3, 7, 2. So for every record, we have again the same thing. We will do the same task again in the second iteration. DT2 will be ready. X and Y splitting is done. DT2 is fitting part is done. Plotting is done. We can see the legend and the decision regions now. And you can see that only one data point is there, which is misclassified now. Have you observed this? So here you can see that there is only a single data point which is there, which is misclassified. It should be inside this region, but it is not correctly classified. So let's try to analyze this in an appropriate manner in the below part by seeing the actual predictions. So here, this is our second DF, which is ready. And as you can see here, what is that misclassified point? I think this is the only one where you can see that the target is 0, but somehow my DT2 model is saying that the prediction is 1. For the remaining part, I can see that all of them are correctly classified, if I'm not wrong, right? So what we have to do, we have to again infer the value of the alpha. Now again, the error is 0.1 because we are getting single error here, single misclassification point here. So alpha 2 will be ready. Now the next step is to again update the weights. So we will update that as per the alpha value as 1.09. Now we will get the updated weights, normalize those weights. I'm doing it a bit fast now because we have done already the same thing in the first iteration. Then we will see the summation of normalized weights. Y is coming to be 0.999. Although it is fine, it is approximately equals to 1. But it should be exactly equals to 1. So we have updated weights ready. Okay. Second DF, updated weights dot sum. I think it is correct. It should be fine. It should be fine. Now we are trying to find out the upper and the lower range. So that we will be in a data frame where we will be having a specific range. It's fine, right? At the end, we are getting just 1.00, right? So we are having a range where 0.0 to 0.05, 0.05 to 0.55, 0.55 to 0.60, and so on. So in this way, we will be having all the ranges available with us. Again, we will do the same task to get the index values. Then third DF, getting that data frame ready with us, right? With respect to the random splits which is happening, random values which my model is giving to me. Again, DT3 is ready, decision regions we can see. And here, one thing which you're observing is again, there is only single point which is mistaken in the DT3. Okay, that's awesome. So let's run this. So what is that point? Again, what I can feel is that this is the only point where the misclassification happened, right? So it is 0 and 1. For the remaining points, no. I think here also misclassification happened. Here also misclassification happened. Here also misclassification happened. Let's examine here also. Here also. So let me go back to the same diagram which we have seen above. Oh, okay. There might be multiple points, but here we are just seeing 1, 2, 3, 4, 5, 6, 7. But in total, we have 10 points, right? So all of the misclassified points. So how many of them are there? Actually, it is 1, 2, 3, 4, 5, 6. Any other point? This is misclassified 1, 1, 0, 0, 1, 1, 1, 1. So it means that 0.6 should be the correct result for this part. Error I'm saying. So let's check that out. So in this, I'm getting the value as 0.6, right? 0, 1, 0, 1. Two data points are there. Then 3, then 4, 5, and 6. So error should be 0.6 in this case. Now let's see the value of alpha 3, and then we can print all of these values, the value of alpha 1, alpha 2, and alpha 3. Because alpha 3, why it is so negative? The only reason is because it contains lot much error, right? That's the main reason. If you remember my previous session, when the error is too high, approximately close to 1, alpha will become negative. Now the time will come where I just want to showcase you. Let's say for now, we're just limiting our discussion to the 3 number of estimators, 3 decision trees, which is DT1, DT2, DT3. Obviously, you can tune the hyperparameters and check that how many decision trees are required in order to get a correct prediction. But for now, you can observe that for discussion per se, for understanding per se, we are limiting our discussion to 3. How can we get that? Via hyperparameter tuning. In the upcoming session, I'll discuss that part. Okay, don't worry. Now, let's suppose, if you remember in our original data frame, right? DF, let's try to print that DF, original data frame that we have. You can see we have 1, 5, right? Let's try to catch up the prediction by the model, final prediction by the model. The target is 1. Let's see that whether our model will be able to give us the result as 1 or not. Let's try to fix it. So what will happen? You will pass this query and check the result via DT1 model. Okay, model M1. You will see that my model is predicting the answer as 1. You will pass the same thing to DT2. Answer is 0. DT3, answer is 0. Okay. So what is happening is you are getting for the 1, 5, the value as 1, 0, and 0. So alpha 1 is 1. Alpha 2 is somehow you're getting a negative result. So you are saying -1. Alpha 3 is also -1. You will multiply all of these things and you will be able to get some prediction. So somehow this code is giving us the result as negative, means it is giving us the answer as 0, which is not correct for now. Let's try to see the result for 9, 9 as well. So what will happen is, so here what will happen, you will just check the sign of this specific result. This is how basically the prediction will happen. If the sign is negative, means our model is saying that the result of 1, 5 belongs to 0, but this is wrong. For 9, 9, let's try to check this out with DT1, DT2, and DT3. Now let's try to examine this. Alpha 1 into negative of 1, but it is vice versa, alpha 2 and alpha 3. Let's try to recheck this result. Somehow it is giving us positive. It is actually vice versa. And here the symbol is actually positive we are getting, right? Let's try to, because it's all about the random thing which is happening, rerun this code again. Maybe getting the updated weights is fine. Alpha 1 is fine. So this is fine. DT1 is fine. Predictions are fine. Alpha 1 is fine. DF is ready. After that, cumulative sum is also fine. Let's recreate this new data set in the second stage. Now we will get some other random samples. Let's see now what we are getting as a result. DT2, X and Y in the second DF. DT2, plotting the region and getting the regions, seeing the second DF. And in this case, again, I am getting only one misclassified point, which is 1, 0, evaluating the error, alpha 2, updating the rows and the weights as per that. And with this, we will be able to get the normalized weights, then getting that range, right? Once it is done, we are again trying to create a new dataset on the second DF, and let's try to see what are the new data points we will be able to capture. Then again, we will try to train our DT3 model on the new set of data points that we have. We will plot that and we'll be able to get the predictions on DT3, right? Let's run this code. Now let's see that how many number of, you can say, points are misclassified. So here we can see first point, second point, third point, and fourth point. Somehow we will be able to capture now 4 misclassified points, right? 1, 2, 3, and 4. Somehow see here that all the target values are 1. So it really depends on that sample data which it is picking up, and this issue is coming because the size of our data is very, very small. When we will deal with the bigger size of data, these things won't happen in this much frequency, right? So here we can just change this number to 0.4. Depending upon that, our value of alpha 3 will now get changed, and then we will be able to get this value, and accordingly we can do our prediction with DT1, DT2, DT3, and accordingly we will be able to get the sign as negative again, which is negative of 0.87. You can just verify that it should be like this, right? So I think that the objective is pretty much clear to everyone. So basically what we are doing in every iteration is we are trying to first of all get the very first iteration done, where we will initialize our weights with 1 upon the number of records, getting the lower and the upper range, and afterwards creating a new set of data points. Every time you will be able to observe that we are getting a new sample of records in the second DF and third DF. The only reason is this random function will give us a random values, and it might happen that the same file, when you will execute, I will share with you, you will be able to get different numbers altogether. And if your numbers, random numbers, focus more on the misclassified points, definitely you will be able to get the correct predictions, unlike the way I'm getting a wrong one, because here might be the random samples which it is picking up is focusing not more on towards the misclassified points rather than focusing on the classified points, because here the size is very less. So even though the range split is huge in the misclassified points, it's not that much huge. And that is the main cause of not getting a correct results. Here you will be able to see it is 268, right? But we are not getting 6 we are getting here, 8 we are not getting, 2 we are not getting. So how will my model will be able to understand and curate a better predictions? But the only point to discuss this step-by-step implementation is just to showcase you that how internally this Adaboost algorithm works. By the way, this process of curating a number of data points randomly, specifically focus on misclassified points in the next iteration, is called as upsampling. Okay? So this is something which you have to make sure. And one important thing in all of these things, whatever we have done, is that whatever value, when you're running your code, it might be the case that I was running it multiple times, so I have forgot to update the error value. Just one thing you have to make sure that whatever value you're getting, maybe this value varies in your case. Alpha 1 though will remain same, but definitely the value of alpha 2 and alpha 3 will be different in your case when you run this file, because your random points will be different. So in that case, whatever value of alpha 2, alpha 3 you're getting, you have to change that value here. For example, this is alpha 1. In my case, alpha 2 is, let's say, after running multiple times, you can just try it your end. What is the alpha 2 you're getting? For example, it is 1.09. So you have to make sure it will be same only in this specific case, so that you will be able to get the correct results as per your records which you're getting randomly, right? Similarly, same thing you have to make sure in the below part, in the 0.4, right? Whatever error you are getting, as per that your value of alpha will get changed, because you know that the formula to get the alpha is 1/2, a natural log of 1 minus error upon error. So depending upon what is the error you are having, definitely the value will get changed. So make sure that you will change that value in the function itself. The parameter you will keep on changing depending upon what is the value you are getting. Now, how can we optimize these results? As you can see that the results are not as much up to the mark. The only goals will be that, first of all, the size of data is very limited where we are working today. Second thing is that, we have not done any hyperparameter tuning. Means we don't know that how many number of decision trees we should apply, how many number of weak learners we should take. For that, hyperparameter tuning will be applicable. If you will just refer the documentation of Adaboost classifier, you will be able to observe that by default, we will be having a number of estimators as 50. Means when we will call via sklearn in the upcoming session this Adaboost classifier, by default, internally, DT1 to DT50, 50 decision trees will work internally. And then only we will be able to get the result. So one thing, data size will be very, very huge. Second thing, number of estimators are also very huge as comparable to what we have used today. So this is something which you have to make sure, right? How can we do that? How can we call via sklearn? How can we do the implementation? Don't worry, in the upcoming session, I'll showcase you that part. But before coming to that session, please make sure that you will try to implement this end-to-end step-by-step part on your own and see what are the results you are getting. Play with these numbers, whatever values you're getting as alpha 1, alpha 2, alpha 3. You can just try to check and verify the predictions of other data set points that you have, which is 3, 6, maybe 4, 8, and verify that what results you're getting, right? Maybe you can try to increase the number of estimators and try to take DT4, DT5 into account and check that at what point of estimators this particular things are going to give us a better results, right? So I hope that till so far, whatever things we have covered up is pretty much clear to everyone. Still, if you have any confusion, any doubts, might be the case, you can just reach out to me, maybe via mail or via LinkedIn, right? So now I hope that you will be easily able to get an idea that how step-by-step Adaboost algorithm works. And this is the literal maths behind this algorithm. But whenever we are working in any industry level project, there is no need to, follow step-by-step how the way I have showcased you. Just like in PCA also, I have showcased you in one video of the course that how internally things worked. And in another video, I have showcased you that how via sklearn you can implement in the real-time projects. So that is what happened to this specific part of the algorithm also. In the upcoming video, I will showcase you that, if you want to implement it directly without implementing these individual steps, so how can we do that?